Okay, let's do an example. So here I've given you in your notes a potential energy diagram. It's already drawn out for the potential for the change in the combustion of hydrogen gas. And there's some questions here that we need to ask. So what is the activation energy for the forward reaction? So reading this graph just left to right like we normally would, remember that I have to get from, let me switch over to drawing mode here, from where I'm starting to the highest point. And in this case, that highest point is positive 50, and my starting point was 0. So that's a positive, because I'm going up the graph, positive 50, and my units are kilojoules. Question 2 says, what's the activation energy for the reverse reaction? Well, now if I'm going right to left, I've got to go all the way from here at negative 241.8 all the way to the highest point. So I've got to go from negative 241.8 to 0, and then from 0 I've still got to keep going because I got to get to positive 50. So this one is a positive 291.8 kilojoules. It's those two combined, because I've got to raise that whole level. Question 3 says, is the forward reaction endo or exo? So forward, left to right, we're dropping, we're losing energy, that's exothermic. For the reverse, we're going up, we're increasing in energy, so that's endothermic. What's the enthalpy change for the forward reaction? So remember, enthalpy change is delta H. It's from start to finish, not from start to highest point, from start to finish. So for the forward reaction, we're going to go from 0 down to negative 241.8. So that's a negative 241.8 kilojoules. And 6 for the reverse reaction, we would start at negative and go up to 0. So that one's going to be a positive 241.8 kilojoules. Like that. So those are the kind of questions that you might see with this kind of stuff. You might be given this graph and asked to interpret it and pull these kind of numbers or information out of it. Now let me show you how this applies. Let me drop out of here to a catalyst. Now you've talked about catalysts probably before in Science 10 or Chem 20. That a catalyst's job is to make a reaction that's probably very slow or requires a lot of energy or really unsafe conditions and allows it to happen much, much faster. Now let's look at why they work. So if we took a normal reaction, let's do a normal exothermic reaction. Here's its curve like that. So let me label this potential energy, reaction coordinate. All right, now we'll call this the uncatalyzed pathway, which just means we don't have a catalyst. So without a catalyst, this is what it's going to take. We're going to need to provide this much activation energy uncatalyzed, and we're going to have this much, oh, I'm a little too deep there, that's going to be our delta H. What a catalyst does is it provides a new reaction or a new way of getting from the beginning to the end, from the reactants to the products, in a way that doesn't need as much activation energy. It creates alternate pathways. So for example, if you did this same reaction with a catalyst, that curve might only look like that. This is the catalyzed pathway. So this delta H is from here to here. You can see how much smaller that makes in this case. So since you don't need as much energy to do it, maybe you don't have to have a big expensive furnace or boiler or something to raise the chemicals up to this temperature, probably making it a little bit more unsafe as well. Now maybe this can happen at room temperature. A good example of this is hydrogen peroxide. So hydrogen peroxide that maybe you've used to clean a cut or a scrape or something in the past is H2O2. Let me write this out. It's H2O2 turning into water and oxygen. But that reaction is very, very, very slow. This is imbalanced. But that reaction is extremely slow. So if you just open a bottle of hydrogen peroxide, it doesn't start foaming. But there are things in a cut or a scrape that are catalysts for hydrogen peroxide. And so that reaction suddenly, instead of needing some fairly extreme conditions before that reaction takes place fast enough, now all of a sudden can happen just with room temperature and your body temperature, and it starts bubbling and foaming and going crazy. Really, it's just this reaction with a catalyst, so now it can occur much, much faster. You'll notice though that the activation energy here did change, but one thing that didn't change was delta H. Even with a catalyst, my delta H doesn't change. The enthalpy, the chemical reaction is still the same reaction. The only thing that's different is it's going to be a little bit faster because I don't need as much activation energy. So because there's less energy required, maybe more molecules can start reacting at the same time, and the reaction is going to take place quicker. That's the idea behind a catalyst. So in your notes, let's see if I can drop back over to here. This will let me. Down at the bottom, I've given another example here. Sometimes a catalyst doesn't just use one reaction, sometimes it uses multiple. So the one I drew for you was just a one-step big curve down to smaller curve. In this reaction, you take the methanoic acid decomposing, and instead of it all happening in one reaction, maybe it occurs in 3 little reactions. But you'll notice that the top of this one, even the highest peak out of the 3, is still lower than it is over there for the 1. So there is a decrease in that activation energy by providing multiple steps. So you may see a graph like that on a question, or if you take chemistry in the future. Don't let it freak you out. Remember that activation energy is always from the start to the highest point. So if there's 3 curves, I don't care about those 2. I only care about that one. He's the biggest. So it's from the start to the highest point. That's your activation energy. And if you're ever looking for delta H, don't even worry about the curves. Delta H is found by only looking from start to finish. Okay? So that covers, I think, everything that you need to know from the notes. But let me show you just how this is used in some normal, like everyday practice. So these catalysts are very closely guarded secrets. If you have a company that's trying to make a product and you found a catalyst that allows you to make it better and cheaper and faster because you found that catalyst, you don't want your competitors to find out about it. So these are really closely guarded secrets in a lot of industry, so you can make more money than the people you're competing with. The next one is the catalytic converter. So this is a little thing in your car. Any modern car anyway has a catalytic converter. You see in the other picture, somewhere between the engine and your exhaust out the back. And what it does is, you can see here molecules of things like carbon monoxide and nitrogen monoxide and unburned hydrocarbons or fuels come in. And we don't want those going out because they're toxic or they contribute to acid rain or all sorts of other problems. But the catalyst here allows those molecules to rearrange so that instead of all those bad things out the backside of your tailpipe, you're getting things more like water and carbon dioxide and nitrogen. Now, it doesn't completely clean the exhaust of the car, but it's much better than it would be if it didn't run through this kind of a honeycomb catalyst on the way out of the car. That's the idea. The other one is enzymes. So if you think about the formula that you learned for cellular respiration, C6H12O6 plus oxygen gives me CO2 and water, that's really a combustion reaction. So for you to get the energy out of glucose, it would really need as much energy as if you took sugar and put it on the table and tried to light it on fire. That doesn't work in the internal human body. We can't have temperatures like that. We would die. So we have enzymes, which are just another way of saying a biological catalyst, that allow us to take that glucose molecule and break it down, get the energy out, and make the ATP that we need without having to raise our body temperature to some crazy thing. Now, in reality, this is that process, and it's not just one enzyme in this case, or one catalyst, it's a whole bunch. So you start with glucose there, and then you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 enzymes there. And if you've taken Bio 20 and you know about turning glucose into ATP, this is just the first step. This is just taking glucose, which is 6 carbons, and snapping it into pyruvate, which is 3. All we did was take 6 carbons and turn them into 3. It took all of these enzymes to do that process for it. But this allows us to do it at body temperature, at a much lower activation energy, so we can be more, both more efficient and also stay alive, which is nice. So these are catalysts, enzymes. These are a part of your everyday life, whether you've ever known it or not. They're a really, really important part of just how we do these chemical reactions in a safe way. So hopefully that all makes sense. You've got some questions in your notes. Work your way through those. Be cautious looking for things like whether they're talking about the forward reaction or the reverse, because that's going to change things a little bit. Remember that delta H isn't ever going to change, and catalysts are not going to do anything too crazy other than lowering that activation energy, but that delta H is going to stay the same. Sorry, that announcement threw me off. Okay, if you have any trouble with it, let me know. We've only got one lesson after this one, and then you guys are done. So push through. Hopefully this all makes sense. But if anything's not working for you, just let me know. Be happy to help you out as much as I can.